It gives me great pleasure to introduce our speaker today, Ron Blakey. Got to know Ron a little bit in the last 7 or 8 years when we've attempted to write a paper together. Hasn't happened yet, but we're still talking about it. But Ron's been busy with some other things. So how many people in the room have used his... You're welcome. Ron did his PhD work at Iowa, taught for a couple of years at Fort Hays State in Kansas, and he went to the University of Northern Arizona, which he was there for over 30 years. Retired about 3 years ago, lives in Phoenix. I think still has a condo or something in Flagstaff, is that right? And so when the weather's good, he goes to Flagstaff, and if not, he can come to Phoenix and vice versa. But we are the first of a series of 5 lectures as an AAPG Distinguished Lecturer. So this is his kickoff, so we're the guinea pigs, I guess. But I'm sure it'll just be great. He's refined this talk for this audience and the stuff that you're interested in. So please welcome Ron.
Well, thank you, and welcome. And boy, I felt very welcome here. I've been carted around to the rocks and the local pubs and everything. So anyway, what's geology without a pub, huh? What I would like to do today, and I asked several of you that I've seen so far about how I might slant this talk, covering the entire history of Western North America in an hour, of course, is impossible, and that's not my point. I hope you realize that that's not my point. I want to show you something about how the maps are made. Not very much, but just to give you a feel for what I do. Believe it or not, there are still a lot of people that think that these are creations out of my head. And yes, I know a lot of geology from my many years of experience, but I don't just sit down and say, well, this looks pretty and that looks pretty and so forth. Then I'm going to go through the history with a series of slides, by time slice, oldest to youngest. And then I will, if we have time, I have an animation, a flash animation, not a true animation. And what I will do with that, it's a new series of maps that most people haven't seen yet. They're a lot more detailed than the series I'm going to show here. So with that, let's get going. I guess the worst thing you could do is apologize on your first slide, but I was supposed to have put AAPG up there, and as I was going through my talk late last night, God, they never sent me whatchamacallit, and it was too late to get it, so anyway, this is the AAPG Distinguished Lecture Series. It's sponsored by the AAPG Foundation, and so please pretend that that's up there, and maybe if I have time tonight, I'll put it on so that the rest of the talks, it'll be there. So anyway, so what we're going to do then is we'll look at a comprehensive history, but the way I'm going to do it, I don't think that anybody else has ever attempted a step-by-step history of Western North America like I've done. Now, I'm not saying, this is all my stuff, and this is the idea of thousands of other people. You have to realize that, and I pull it together. But when you think about it, when you read a paper, usually it's focused on an area, or it's focused on a time, or several time slices, or whatever. And so what I try to do is pull this all together into one cohesive, hopefully, model. So I follow modern geologic concepts. I think this is important. If we show a plate going from point A to point B and it breaks all the plate tectonic speed limits, something's wrong, right? So we have to follow the geodynamic principles, and I try to put this in a way that is understandable to geologists like yourselves, to people that know a little bit about geology, or to people that know, in some cases, virtually nothing about geology, because most people have a fairly good concept of what a map is and pictorially what it's trying to show. Okay, so how do I prepare these maps? Well, I gather as much data as I can. And this is very time consuming. Frankly, it's the least interesting part of it. I'd rather make the maps, but it's a step we all have to go through as scientists. We have to gather the data. The conclusions and the summary is always the most fun, not necessarily gathering the data. Constructing the base map is a very tough chore, deciding on the resolution, what projection I'm going to use, the scale, how many time slices am I going to choose and what will they be and so forth. Usually I start by plotting the tectonic elements on each time slice. Those are, in a sense, the first order things that sort of control the distribution of geologic phenomena, the plate boundaries and subduction zones and et cetera. I plot the shorelines, and I've gone back and forth over my career of making these maps of just how to show the shorelines. And finally, I've settled in the last several years, so my newest series, what I tend to show is the high stands. These are believe it or not, they're the easiest thing to show. Low stands are very difficult to show. But the high stands, so most of my time slices show the high stand for that particular time slice. I plot facies, depositional settings, climate zones, and so forth, because I can adjust the maps in Photoshop. Everything is done in Photoshop, which is a pixel-oriented or a rasterized program. So it's not shape files or anything like that. And so I could change colors using various tools in Photoshop. So if something looks a little too humid and I know it was a little more semi-arid or arid, I can bring out some browns and so forth and vice versa. And the way I get my maps together is I clone modern topography. If you use the clone stamp or the rubber stamp tool in Photoshop, you know what I'm talking about. It's a very powerful tool. And so I clone modern topography from modern DEMs. I use GeoMap app that you may have heard of. If you just Google that, it's an incredible site in terms of getting maps and so forth. And then, of course, the last stage, which sometimes drives me nuts, is checking and rechecking, and I find an error, and I got to make a major change to a map that I spent hours and hours on, and anyway. So, but sometimes that last step is as time-consuming as almost all the others. So, okay, where do I get my data? Certainly from various terrain maps that are published, plate reconstructions, there's a lot of those out there. Structured tectonic maps, particularly ones that show broad areas and show sequences of time. Those are the most useful to me. Palinspastic restoration maps. Restoring these things can be a nightmare as well. I'll talk a little bit about that when I get to some of the maps. Various facies maps, paleoclimate maps, faunal floral distribution, and of course the list could go on, but I think you get my point here. So I'm going to run through these real quick. I just want to show you there's a lot of data out there. The details on any of these doesn't particularly matter. Stamfley and Borel have done quite a series of plate tectonic maps. Here's one of them, I think, in the Devonian. Tanya Atwater's big movie, you can download this off her website. You see Santa Barbara. And this is great for showing the history of southwestern North America over the last 40 million years. Here, I just took a time slice at about 32 million years. The famous Silberling terrain map that shows the terrains of western North America. So any story that I tell you has to end up here. Has to. Because that's where the things are today. I can play around with, I took the stripe map of the Atlantic Ocean with all the age, and what I did is I cut out everything older than 84 million years and pushed the two plates together, so that's what the North Atlantic looked like 84 million years ago, whatever. You know, I could have chosen any time to do that, but things like that. An invaluable site are Ziegler's paleotectonic maps of Europe and Eastern North America. The amount of data on here, these may look fairly simple, but when you study these things, that's an incredible amount of data. So maps like that. This is an interesting story. I took the California, there's a beautiful map online of the geologic map of California, digitized. Okay, I took it, I had to copy it in slices and then put the slices together. And then what I did is in Photoshop, I sliced it up and I moved the plates following the faults, and I moved them back to what we think things look like in the Miocene. So this is the California map moving back to the Miocene. And so the Miocene deposits are kind of this medium yellow. It doesn't show up real well here, but there's a medium yellow color. So that's the Miocene. And so I can see where the Miocene deposits are. They show continental versus marine. And so then I can take this map and overlay that information with a very simple paleogeologic map. There's the uplands, there's the continental, there's the marine, there's some of the islands and so forth out there and so forth as to what it would have looked like in the Miocene. So that's another trick that I can use, is cutting up and redistributing. The volcanic facies maps in the DNAG volume, Christiansen and Yates, the best thing I've ever seen for showing the distribution of volcanics in Western North America. Solibi and Busby-Spera did a DNAG volume on the Triassic and Jurassic of Western North America. This is basically Silberling's, the map I showed you a few minutes ago. They're taking it back to the Jurassic. So there's a paleo reconstruction back to the Jurassic. Dickinson's palinspastic restoration, he's done the best palinspastic restoration I know of, because he takes into account both the severe orogeny shortening and the basin and range extension in making these maps. And that's not an easy chore at all. The Macquarie and Warneke maps of the evolution of southwestern North America over the last 34 million years, they have about 20 time slices. I've shown 2 of these. These help a lot in trying to detail how the continent extended. Some sort of cartoonish looking maps, but again, a lot of information on these done by Jim Monger up in Canada. I don't know that he's published these yet anyway. He gave me these maps several years ago showing the Canadian version, which sometimes we ignore. And as we'll see in a few minutes, a lot of Canadian history took place off the coast of the western US and now has shifted northward. What do we got here? The old Shell Atlas by Cook and Bawley, still an incredible source of information, even though it's 1975. Again, the amount of information on here with facies and isopachs and so forth is really another one of my favorites. 1972, yeah, that wasn't quite the Pleistocene. You may think it was, but this Rocky Mountain Atlas, the big red book, there must be one floating around here somewhere. Somebody must have one. I still have mine. It's falling apart at the seams. I mean, the book is literally that big. And that facies material is still pretty good. I mean, they've redone things, but it's still pretty good. Kirkland and Elder's reconstruction of the Cretaceous, they've done extremely detailed restorations of the various, here's several of their maps here in the Cretaceous. What do we got here? The DNAG Canada volume showing, what are we in here? Late Cretaceous of Western Canada. Here's a paper by Arthur and Sageman that shows paleoceanography of the Western Interior Seaway. This really helps because now I know the current directions and how the water was moving, so this can influence how I show a shoreline, which way the deltas bend and so forth. Some maps that I got from the literature, much of this I stole from none other than Chuck Cluth, of putting together the history of the various basins and uplifts of the greater ancestral Rocky Mountains. So here's the basin history, and you can see these basins are subsiding and being positive at different times, even though they're all part of the same ancestral Rockies system. And then here's the uplifts, and you can see the time of overlap when the yellow material starts showing. That's when those uplifts were buried and so forth. So This really helps in making these maps because I got to pay attention to this kind of data and show mountain ranges disappearing at the right time and so forth. Putting paleoclimatology, overlying it on some of my maps. This is some of Judy Parrish's data that I put on my Permian map. Boy, does it fit the geology absolutely perfect. The wind directions are right. There's Aeolian rocks up here in England that match up just perfectly and so forth. So that kind of information. Here's the 2004 time scale. I put some of my maps, I posted them here so we can see how the time slices match up with the accepted international time scale and so forth. Okay, so with that background, let's go ahead and look at the, how much are we doing with time here? Let's go ahead and do this time slice through the Western North America. And again, the way I'm going to do it, I think I have at least somewhat of a feel for the audience here. And so I'm going to, there'll be some I'll skip over fairly quickly, and there'll be others that I'll spend a little bit more time with. Okay, I'm going to do the 30-second, actually probably a minute and 30-second, the quick history from Cambrian to present. So we start out with the familiar passive margin. Where's my light? With the familiar passive margin. Sometime in the middle Paleozoic, an arc system approached Western North America. Its collision began in the latest Devonian or earliest Mississippian. It's interesting that the signature that these colliding terrains carried don't match anything in North America, so they're clearly exotic. More on that later. We get, after these arcs accrete, we get a reversal of subduction, and we get a west-facing arc. We steepen subduction, the back arc spreads, we get the famous Havala Basin of western Nevada. The arc recollapses in the Permian when subduction becomes less steep again, and we form the Sonoma orogeny. And then that collapse continued into the Triassic. Somehow the arc was duplicated. There's a lot of theories on how that arc was duplicated. I think in the southern part of the western interior, or the southern part of western North America, it was probably duplicated by transform faulting. So the arc actually was transformed out and you get a duplicate arc. But it looks like during the Triassic and Jurassic we have at least two arcs out here. Things get very complicated. Between these two arcs then we end up with some exotic debris that came from Asia. How in the world does that get in there? And then in the Jurassic, another exotic terrain, the big one, Wrangellia, starts approaching, causes the arcs to collapse. We accrete Wrangellia, it moves southward. We call it Baja BC. I may have time to get into that a little bit later in the talk. Then it moves northward again and goes up to its present location at Vancouver Island and further north along the Alaska coast. Then we get this thickened slab being subducted under western North America. This is what really changes the picture. I'll spend some time with this in the map view, but this thickened subducted crust raises havoc with western North America, creates a number of features, including, we think, the Laramide orogeny. And then we get a flat slab subduction into the Cenozoic. Eventually the subduction steepens and we get a transform fault when the East Pacific Rise intercepts western North America, and we get various terrains moving now northward, right lateral transform faulting, and of course the most famous fault is the San Andreas. Apparently the slab breaks off, and I think that people that do mantle tomography, I think they have this under Kentucky or someplace back there now. But anyway. Okay, so when we look at the maps, just a brief introduction. You'll see this tectonic map on most of the screens, and these are the kinds of features that I try to show. The various tectonostratigraphic terrains, the plate boundaries, the structural features. On some maps I'll show shorelines, on other maps I won't. Labeling a lot of features, telling us what's happening and so forth. Some maps will show thickness and some won't, and so forth. So you'll see this map, and then you'll see it paired with this map. And these are the paleogeographic maps. And this is the same series I notice you have in your hall here on those posters. So you'll see that same series. And again, I don't think with this audience I have to go over what most of these features mean, but anyway. So let's look at these time slices. So here we are with the passive margin that occurred for several 100 million years in the late Precambrian into the early to early middle Paleozoic. Things were reasonably simple compared to what's going to happen later. One little twist that I really like, that I really feel was going on in Western North America, is there is probably a series of blocks that, like Madagascar is today, where it rifted off with India and then broke away from India and got off several 100 kilometers into the Indian Ocean and is perched there off the coast of Africa. These blocks have been well documented in the Appalachians, and I think they help explain some of the orogenies in Western North America as well. We don't know the exact location of these. These are somewhat hypothetical, but I think that they probably were out there. I think, for example, this helps explain why the antler orogeny is more severe in certain areas than it is in other areas. I think these blocks were helping to dampen that orogeny. So, speaking of the antler event, a series of arcs came in, and there's two fairly recent papers that discuss where the antler orogeny material came from. One suggests it came down from the north because these terrains carry a lot of Siberian affinities, detrital zircons and fossils and so forth. Baltic affinities. Baltica is the North European craton, and it also has some affinities from, let's say, the Taconic orogeny, which of course is famous in New England. So how in the world does this stuff get to Western North America? Well, Colprin and Nelson with the Yukon Geologic Survey feel that it came down something like this. At about the same time, a paper by Wild and Wright at the University of Georgia, they think that it's better explained by material coming from the south. I took both views and show them on my maps, but you don't need both. Maybe neither is right, but I think it really helps explain. I think it's better than taking it all the way around through the Paleo-Pacific or Panthalassa. I think it makes a lot better sense to, because we have traces of this stuff all along eastern, southeastern North America, all the way up in the Canadian Arctic. So to me, the trail is there, and that's what these authors saw. So they collide and form the antler orogeny. The subduction zone flips then, so it becomes west-facing, and then we get more normal west-facing subduction off in North America. And anyway, I think that particular model, I really had problems doing the antler orogeny. And when I saw those two models, I've sort of stuck by them. I like them. During the Pennsylvanian, then, we get what happens when a subduction zone starts to steepen. It starts to pull the upper plate apart. It causes it to extend, right? So when it extends, we get back arc spreading. If that back arc spreading goes far enough, we create an ocean basin there. And I think that's what the Havala basin of western Nevada probably is. I shouldn't say that's what I think. This is what a number of people that have worked out there think. And then up in Canada, it's called the Slide Mountain terrain, or the Slide Mountain Basin, or Slide Mountain Ocean. So this back arc spreading continued through the Pennsylvanian and into the Permian. And then the arc started reversing. Why would an arc reverse? There's several reasons. The easiest way to get an arc reversing is shallow up the subduction, so now you push things back towards the continent. It's not the only way, but I think it's the simplest way of doing it. So the subduction shallows, they start moving back towards the continent, the subduction angle briefly changes, and we close these two basins and create the Sonoman orogeny. So keep in mind now, these terrains have accreted, spread off, and now reaccreted again. And it's these terrains like the North Sierra, the East Klamaths, that contain the stuff from Europe and Asia and so forth that couldn't have come from North America. There's some age dates that just absolutely could not have come from North America. The Triassic and Jurassic become very, very complicated. I think you're getting the picture of these accreting terrains. I'm not going to go into great detail here, even though I think these are some of the most interesting arcs that we've ever had in our geologic history. Maybe two, maybe as many as three arcs off the coast of what is now Northern California. We don't know the polarity of many of these arcs. Some of them seem to be derived from North America. Some of them have more exotic material. But in between, or sandwiched in between these various arcs, is this famous McLeod fauna, which it comes from a fauna that the closest place to North America it is today is in some part of China. So somehow we brought something across the Panthalassic Ocean, and it got sandwiched in between these various arcs. And this is what we call the famous Cache Creek terrain. Many of you probably have heard of that. And up in Canada, it looks like the arc swung back on itself. It did a dipsy-do and with an oroclinal bend, and here's the Cache Creek Ocean. Whereas I think probably further south off of California, it's better explained by transverse faulting of an arc, duplication of the arc that way, and then collapsing against the continent. So take your pick on those various models. They're all out there in the literature, as well as several others. By the early Jurassic, then, this is where we really start to get a complicated series of terrains. And to make things more complicated, if you watch to the left of the screen, oops, okay, I got a Middle Jurassic slide here without a tectonic map. Just because this is kind of interesting, it shows the opening of the Gulf of Mexico in the early part of the Middle Jurassic. The return of the Western Interior Seaway. I should have mentioned that the Western Interior Seaway withdrew through much of the Triassic and early Jurassic. It returns again. And again, these very, very complicated arcs off of Western North America. Then, there we go, to the left, another terrain is approaching, this massive, very complicated arcs, and somehow obliquely colliding with these arcs, slamming them together and crunching against Western North America. And the timing of this is just about right when the first phase of the Nevadan orogeny took place. So I think there's a strong correlation between the accretion of Wrangellia. I'm sure, as most of you know, Wrangellia is absolutely exotic to North America. There's several ideas where it came from. Again, probably Baltica or somewhere up in the Arctic or what have you. But it is not North American at all. So, okay, so we're going to collide this block. We're going to fuse all these pieces of arcs and inner arc basins out here with this collided terrain. And this newly assembled block has been called Baja BC, or Baja British Columbia. Why is it called that? Because it's thought that what is now British Columbia, which is the west coast of British Columbia and Vancouver Island, at one time were down as far south as the latitude of Arizona. So how could that happen? Oblique plate collision taking place here. I guess my arrow on this plate is cut off the screen here, but anyway, very oblique collision starts driving this Baja BC southward. How far south it came is very, very controversial. We tend to favor, I've worked with a colleague, Paul Umhofer at NAU, and we favor it coming down to about northern Arizona latitude, something like that. Others have taken it all the way down to here. Others would suggest it never got north of the present California boundary. So regardless, it collided, it accreted, and it moved at least some distance towards us relative to the rest of the continent. And lo and behold, at this collision and starting to move south, what happens there? The beginning of the severe orogeny. So again, I don't think it's a coincidence. I think the severe orogeny is partly driven by this collision with Wrangellia and Baja BC. And then by the mid-Cretaceous, it's about as far south. I probably have a little further south in this particular map than I might pull it a little further back to the north, but it reached a distance south. This has some problems with California geology, there's no question about it. And I give a talk next week in Berkeley, and I'm sure I'm going to hear about this, but so notice the Western Interior Seaway. And here's an interesting point that I know a lot of people in this room are interested in. This is the so-called mid-Cretaceous, the Cenomanian, just about exactly 100 million years ago. A lot of rocks out there of this age, aren't there? Including right out our window here. At that point, there was a barrier across New Mexico and West Texas separating the Western Interior Seaway from the Gulf of Mexico. What happened just after 100 million years was maybe the biggest, let me get it right, OE, the oxygen minimum event, whatever, in the Atlantic Ocean occurred just after this, right? So we have all this junk sitting in the bottom of the Atlantic Ocean with no place to go and moving along, almost poisoning the bottom of the seaways, if you wish. But we see that at this age, we see this stuff down in Texas, but not in the Western Interior. But guess what? The most rapid sea level rise, perhaps, of all geologic time is taking place starting about 100 million years ago, and bingo! We jump this barrier, and that input of highly organic material comes into the Western Interior, and there's our first big dark black shale. So again, coincidence? I don't think so. I think the paleogeography and the interpretation of the paleogeography and the paleotectonics is telling us something here. These things don't just occur. They're based on global events. So anyway, and I should point out, here's this big slab coming in to screw up the subduction zone off of what will become Southern California, Southern Arizona. As it subducts, it creates incredible metamorphism in what is now Southern California, the Rand, Polonia, Orocopia, I'm forgetting one of the schists anyway out there, that were the metamorphic results of this event. Basically what happened is you take this slab, sucked the Franciscan Four-Arc Basin down with it, and the Franciscan was taken down, I think I've seen on some diagrams, to at least mid-crustal levels, and then the whole thing popped up. And so now you get Franciscan showing up as these incredible schists across Southern California on both sides of the San Andreas Fault. The San Andreas has, of course, subsequently rifted them apart, but on both sides of the San Andreas. So the Orocopia, the Rand, the Polonia, and there's another name that I forget. That's when they're occurring. So during the late Cretaceous, then, we get a series of transgressions and regressions. When I get to my animation, you'll see these transgressions and regressions during the Cretaceous. They show up really nice on my maps. And so here's the subducted slab, the very tail end of it. The subduction zone builds out west of it, and this is what wreaks havoc then, and ultimately is going to create our laramide orogeny. And so the flat slab then takes this thick material all the way under the Colorado Plateau and the Rocky Mountains, and its leading edge, if you're familiar with the volcanic pattern during the late Cretaceous and the early Cenozoic, what does it do? It jumps inboard fairly rapidly, following the leading edge of this slab, so that it doesn't show up very well, but this pink is volcanism, and in fact that's the age of Table Mountain out here, more or less. Where are we here? We're Paleocene, Eocene, okay. So we get the Colorado mineral belt, et cetera, formed by this leading edge of this thickened slab. And then we plane off the severe orogenic belt and form a feature called the Nevada Plano, which probably was like the modern altiplano of the Andes. If you've looked at maps, you see this area right in the middle of where the Andes are their widest. It's almost flat. Similar to the Himalayan plateau also. Big, huge uplifted area that has very little local relief, but is at very high elevation. And so they've done a lot of studies. They've shown that a lot of detrital zircons in our Cretaceous rocks in the western interior came from this Nevada plano. At times, they can pick up detrital zircons coming from the Sierras. At other times, the detrital zircons did not come from the Sierra. So they have a very good record of where the sediment that fed the western interior Cretaceous seaway, where it was coming from. At other times, it came from southern Arizona, what we call the Mogollon Highlands down there. So very interesting patterns in the Cretaceous. It's funny, I spent most of my career making fun of the Cretaceous. I said, the rocks are so ugly. You know, these Triassic and Jurassic rocks, you know, it's no coincidence that's where they put the national parks. But I'll tell you, the Cretaceous has to be the most interesting geologic period in the history of the planet. It just has to be. It's just the things that went on. And again, I still love my Triassic, Jurassic, and Permian, but man, what a time. So, okay, let me slow down here for this early part of the Eocene, because again, I know a number of you are very interested in this event. And the Laramide orogeny, keep in mind that it took place well inboard from the edge of the continent. There was no outlet from the western interior until, I guess, about middle Wilcox time, something like that. Sometime in the Eocene, finally, some of the sediments made it to the Gulf of Mexico. Nothing was going to the west. Everything was shut off. And so whatever was happening between these Laramide uplifts is basically trapped between them. And of course the basins were subsiding at the same time. So this would show, this is a little, as I remember, the peak Green River is about 48 million, something like that. But anyway, so this would show the Green River lake systems at or near their peak. And of course, they went through a saline phase, they went through an organic phase. I don't know if it still holds. Some of you probably know this. There's more organics there than the entire Middle East. Is that still true? I'd heard that. An incredible trap of organic debris in these huge lakes. And when you superimpose this over, let's say, the modern Great Lakes, it kind of makes them shrink. I mean, these were huge lakes. Maybe not real deep. I think there's some debate on how deep they were, but at any rate, they were very, very large, and they accumulated an incredible amount of sediments, including virtually all the organics from the western interior that was trapped in there. So, okay, so the lakes dry up in the later part of the Eocene. We start to see the East Pacific rise starting to approach western North America, and of course, this is going to be probably, we could argue whether the Laramide event or the interception of the East Pacific rise is the biggest single event in western North America history. Take your pick. But basically, the Pacific rise starts intercepting western North America. We go from a subduction system to a transformed system, and we continue with subduction, but as the transformed system proceeds, I think it's maybe the next map, one more map, we start to break up the subduction system, turn it into an early transformed system, and the slab breaks off. And like I say, I think the tomographers are telling us that that slab is somewhere under the mid-east of the United States now, somewhere out there. So now what's going to happen? Because the Pacific Plate is moving northwest relative to North America, and it's moving about 5 times faster than North America, we're creating a hole in the mantle. Well, that's not allowed. We got to obey our rules. And so how do we obey our rules? We stretch the crust of the North American plate and pull it southwestward, and we start extending western North America and create the early phases of the basin and range. By middle Miocene, we're starting to see the basin and range. This is the time right here of the Monterey Formation. This is another, I heard someone say, not too long ago that overall the Monterey Formation has produced more petroleum than any other single geologic unit on Earth. Again, take it or leave it, but it's produced a lot. A lot of oil companies started out there, right, Chuck? Looking at the Monterey. Look at the setting for the Monterey. No wonder, I'm sure some of you have seen it. It's different every place you look at it. Well, look at the paleo setting there. Deeper water, shallower water. Some of these blocks are going to go off on the Pacific plate. Some of this of course is going to stay with North America up here. And then add to this the incredible upwelling that a lot of people think is responsible for the organics in the Monterey, the upwelling that still is going on today off of Pacific North America. And then we start doing really interesting things with the transverse range. It was down here on the last slide. We start rotating it 120 degrees clockwise. We open more basins for the Monterey to be deposited in. And then as we start getting into very modern times now, the San Andreas Fault is going full tilt and moving the Baja and the rest of the North America that's attached to the Pacific plate to the right, so that we can say that LA will be a suburb of San Francisco or vice versa, and you can calculate with present rates how long that will take. And continue to rotate the transverse range, and finally that brings us to the present. Okay, well let's, just a couple of conclusions here before I show the animation. I think you'll agree that the history that we've been looking at has been a bang and not a whimper for the most part. Although one of my favorite quotes in all of geology was by Derek Agner, a famous British geologist, and he said, "The geologic record is like the life of a soldier, long periods of boredom separated by short periods of terror." And if that isn't the geologic record. So I think the events I've shown here, I think it would be impossible to string these together unless you use a method like I use and go time slice by time slice by time slice. And so I might be halfway through the Cenozoic, and let's say I take my Miocene and take it back to the Eocene, and I say, wait a minute, these two things haven't moved yet and they don't match up. I've got a mistake. So then I have to go back, I have to move everything, which in Photoshop is not easy, because remember, I'm not dealing with polygons, I'm dealing with pixels. So now Photoshop has a lot of powerful tools. The warp tool, if you've ever used that, is that fun. You can warp things all over the place, and believe me, I use that on these maps all the time. So, but I think that that's how we can try to understand. It doesn't mean that this model is right start to finish, but it means that you can come up with a comprehensive geologic story if you put all the events together and follow basic geodynamic principles. And of course, we use modern topography because we think that much of the Phanerozoic had topography something like we see in the modern. There's no reason that a collisional mountain range in the Paleozoic wouldn't look something like the Caucasus or the Himalayas or the Alps today. So now we got to be careful because we don't really know the glacial history of some of those ancient mountain ranges. And of course, when you look at modern mountain ranges, many of them are dominated by glaciation, which may or may not have been in the past. Although I just saw a paper a couple months ago, that they found really good sized glacial deposits in the Pennsylvania and West Virginia coming off the Appalachians. Kind of cool. Okay, so let's see, I hit escape to get rid of this guy. Oh, the Q, of course, QuickTime. Alrighty. You never knew I did this for 35 years, would you? Okay, well let's, what I can do is I can go through at slow speed and then faster speed and so forth. And these maps, by the way, they don't completely match the series I just showed you. These are newer. They don't show as large of an area, but they're much more detailed. I think you'll see that right away. And so we'll go through these, and what I'd like to do is, on these maps, you'll see some of the details of the basins you're interested in, and I'll pause them when we get to some of those times. And I think we can see that why a lot of these black shales are distributed the way they are by looking at the paleogeography. Okay, let's go double time through part of the Paleozoic here to, we'll just see the seas coming in the Cambrian here. I thought I hit 2x. Is it moving? That runs faster than this on my computer, but it may just be the system. You know what I can do? Okay, I see it moving. Okay, there we're in the Ordovician. You've heard of the Eureka quartzite out into Nevada. There's that big swatch coming down from the Canadian Shield all the way out into Nevada. Here we are in the Silurian. There's no Silurian in our part of the world except for those silly diatremes up in northern Colorado that the sea had a fit there. Okay, let me start to, okay, early Devonian. Watch the transgression. John, there's your channels that we were talking about this morning. Okay, so let's go into, okay, there's the middle Devonian transgression. Come on. Okay, so we start to get some restriction. This doesn't go far enough. This series doesn't go far enough to show the Bakken. But basically what's happening is we start to restrict, as the seaways are coming across the transcontinental arch, there are various highs and lows, and darn, I forgot that this didn't go quite to the Bakken, but we get, obviously this isn't the Bakken, this is north central Colorado, but we get a restriction, something like that during Bakken time. The interesting thing that I found about the Bakken, and I don't claim to be an expert, but I've read a few papers on it, and that is, like most of these black shales, number one, they follow a rapid marine transgression. Number two, they almost always, not quite always, but almost always sit on a shelf carbonate, right? Number three, which unfortunately this slide doesn't go far enough north to show the Bakken, but they're surrounded by 2 or 3 sides by topography, not necessarily high topography, so they're restricted. Number four, during high stands, they have a direct opening to the global ocean. During low stands, they may have been shut off. I think there's still a lot of debate on that, but at least during high stands, they had a direct connection to the open ocean. So things got funneled in there. Even if you have a nearby uplift, if you got a transgressive sequence, what does that transgressive sequence do to your shoreline deposits? It traps everything at the shoreline. That's what's happening today in the North Atlantic. Very little coarse materials getting into the Atlantic off of eastern United States because of the Pleistocene transgression. It's all being trapped. We get relics and palinspastic sands offshore, but we don't get much sand being supplied directly out onto the shelf at present because the transgression traps everything in Chesapeake Bay and all those other bays and all the bays of South Carolina and Georgia and so forth. So here we're going into the Mississippian. Oh, is that it? Okay, yeah, it isn't going as... Is it going faster now? Okay, there we go. Okay, let's go a little further here. Stop. All right, what's happened here? We just went through following the Mississippi and Pennsylvanian boundary. We had a big landmass across the transcontinental arch and most of the Southwest. During the early and middle Pennsylvanian, we get this transgression. What's the transgression doing? It's going into rapidly subsiding places like the Paradox Basin. What's the Paradox Basin full of? It's full of 2 things. It's full of salt and it's full of black shales. So depending on sea level and what the influx and outflux of the various ends of the basin are, you're going to get one product or the other, because keep in mind this was a really arid climate through here. This yellow, it's not showing up very well on this projector, but the yellow here, these are all aeolian sands. And I've documented, this is work that I've done myself. A lot of what I've shown you, I've gotten from the literature. This is work I've done myself. I've worked an awful lot on the Supai group and the Cutler group and so forth on the Colorado Plateau. And so these aeolian sands all have signatures that came from the north and the northeast, including signatures that come from Devonian and Mississippian rocks that are nowhere in western North America, that had to come from the plutons and the batholiths in the Appalachians. So we have transcontinental river systems supplying our sand from the Pennsylvanian through the Jurassic. And this is shown without a doubt by the detrital zircon work of Garrels and Dickinson. If you've seen those papers, they have a series of papers, some very detailed, some very broad, and they show these things. So here's the Paradox Basin, and here's the western Colorado, the central Colorado Trough, the Eagle Basin, whatever you want to call it, behaving much the same way. And of course, the Eagle Basin is famous for all the evaporites, all the wall board that comes out of there, and so forth, or at least used to come out of there. So let's zoom through the Penn Perm here, and we'll see the seas come in and out through the ancestral Rockies. There's a high stand. Now there's a low stand. See, the low stand allows the aeolian sands to cross the basins. There's another high stand. And then we start to get, in the Permian, the sand just overwhelms the system. And the aeolian sands come in from the north again with the signatures from the Appalachians, the Canadian Shield. And we get these, that was the Weber and the, let's see if I can stop on Lyons time here. 280, let's go one more screen. Yeah, that's probably close to Lyons right there. So your famous Lyons sandstone up in here is about this age. At one time I knew exactly which unit it correlated on the Colorado Plateau, but I think it's sort of middle late Leonardian. Okay, I'm going to stop at the next big transgression here. There it starts. That's the Torweep Formation of Grand Canyon. There's the Kaibab. Let's stop there. Kaibab Park City. Phosphoria. What do we know about that? Another rapid marine transgression over carbonates, black shales. So the Phosphoria was a very complicated system. I don't know that much about the details of it, but it certainly seems to match. Up here, there were a lot of restrictions. There may have been more islands than I show here. There was a high in Montana and so forth. So the Park City was fairly restricted, and the equivalent Phosphoria. We don't get the organics down in the Kaibab, same seaway down here, maybe because it was completely open across there. So we get the chert down in the Kaibab, but we don't get the phosphate or the black, the dark shales. Okay, let's zoom through the Triassic and the Jurassic. In the western interior, there's not a lot of petroleum deposits in these rocks. There we are. There's the Permian high stand. There's the Moen-Kopi-Thames transgression in the early Triassic. Chinle time. Chinle, Paposia, probably your lichens, maybe. I want to stop here real quick. I did a lot of work on these rocks. This is a system that we've traced all the way across the plateau, a major trunk system, and it was fed by a series of streams coming from the southwest. This is the famous Sonsela member of the Chinle Formation. This is the petrified wood bearer. So this is the first influx into the western interior of major detritus from the Cordilleran Arc. This unit is full of volcanic, both ashes and the coarse-grained detritus material. All right, let's scoot up to the Cretaceous here, through the Triassic. Come on, go, 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 go. Let's go a little faster. I like the red beds, but I suspect many of you aren't as interested in them as I am, so we'll zoom through them. Glen Canyon time. There's the Great Navajo Erg right there, expanding all the way into the arc. See the colors up here just aren't coming through. There it is going all the way into the arc. Here comes the Middle Jurassic seaways, the Sundance Sea, the Carmel Sea, whatever you want to call it. Here's Morrison time. The rivers reverse and now start flowing completely off the Cordilleran and southern Arizona. The lakes in the Morrison. There's the lower Cretaceous, and now I'm just going to run it through the Cretaceous seaways, and we'll see the seas come in and out. I've got a high stand and a low stand for each of the Cretaceous cycles here. There's the Bisbee Basin there in southern Arizona, the opening of the Gulf of Mexico. Notice that the streams, the lower Cretaceous streams, are paralleling the severe front. There comes the seaway breaking across in the early Cenomanian. There at Seal, there's the Seal now, across Texas and New Mexico, which keeps the Gulf from. There's the breakthrough in the Turonian, and that's the first big dark shale in the western interior. There's the Farron regression. There's the Bluegate Emery. I don't know if these names mean that much to some of you, but anyway, there's the transgression. There's the regression we see along the Book Cliffs, another transgression. Where are we here? Santonian. So we're late Niobrara time, I think. Now we're into the Campanian, and there's the sands at Mesa Verde across the Four Corners. Another transgression between the two cliff-forming sands at Mesa Verde. The regression, and there we're getting into the early Maastrichtian, and finally the seas leave. I'm always trying to find out whether those seas left to the north, south, or both. There seems to be a debate on that. There's the lakes forming in the Cenozoic. There's the height of the Green River. Lake Gashut, the North Lake, dried up before Green River Lake did. There's the Piceance or Pissance Basin, however you want to pronounce it. It's Pissance, I'm sorry, that's what it is. There's the Oligocene, sand dunes across the Colorado Plateau in the Oligocene, probably into the northern and central Rockies as well. There's the East Pacific Rise intercepting western North America. You're going to see western North America. Now you're going to see western North America grow. See it grow there? It's going to expand, bang, keep going, expand. The rotation of the transverse ranges, early Pliocene, Miocene, Pliopleistocene. I'm going to pause here. This, for you glacial fans, you can't believe how long this map took to make. I found every Pleistocene lake deposit that I could find in the literature, and hopefully they're all on there, I don't know, but the glacial, of course, is subject to exactly which phase of Wisconsin glaciation are you talking about, but I'd like to think that's probably close to maximum there. And so, anyway, that was an interesting map to make. And then, of course, there we are at the present, and I'll just freeze on the present. And so, there you've had 550 million years in 62 minutes.
What do we do about Scott's pub? Is it gonna be-
Let's do like 2 questions. Just a few questions.
And I'm willing, yeah, if people want to stay around, I've got the rest of the afternoon. So.
Two good short questions. Really neat ones. Okay, I got a good question. You only get one. On what? One at a time. Oh. Okay, that's easy. The global scale one. When you build up your model, build up your map, you are dealing with different, theories or models.
That's my timer telling me my time's up. Excuse me.
So there's always some arguments between scholars, those paleontologists, and
right.
those who are dealing with paleomagnetic data, who are dealing with infrared zircon data. They have all different models, back to like the early Paleozoic.
Sure.
Or early.
Or even late Phanerozoic, or late Proterozoic, yeah.
So I was wondering how do you deal with those arguments? Do you have any preference for that, or I mean, usually could come up with one version of.
Right, right. Okay, that's a really good question, and believe me, it's not easy to answer, because eventually I come to the fork in the road, and I mean, I think that's what you're getting at. Which fork do I take? And usually I'll try to stay to the fork that keeps me on the general trend that I'm trying to show. Now, in some cases that doesn't work. When I make a map, then I have to choose one or the other. But in some cases, let's say I'm heading off in this direction and get to a fork in the road. Well, if I take this fork of the road, it really throws the trend of my maps off, and I stick to this trend. In other words, I'd have to go back and readjust all my previous maps to make them fit this new terrain model in the late Cenozoic, let's say, whatever, wherever we're talking about. I mean, a good example of that is something I glossed over here, and that was the accretion of arcs during the Triassic and the Jurassic. There's at least three major theories on that. The one is the repeating of the arc by transform motion. That's Jason Salibi's idea. The second is the Canadian idea with we repeat the arcs by oroclinal folding. And then the third is Ray Ingersoll and Schweikert and that camp of geologists. They say it's all exotic. None of this is North America. Well, I don't, too many people tell me that there's too much North American stuff in some of those Jurassic arcs that you can't make it all exotic. You can make some of it, but you can't make all of it exotic. So, I mean, I respect Ray Ingersoll's work a lot. In fact, if you followed some of his earlier papers, this kind of follows his general trend, except for in the Jurassic, it really varies from he wants everything coming from the Paleo-Pacific. He matches every phase of the Nevadan orogeny to a new incoming arc from the Panthalassa, okay? I just don't, people tell me that no, that just doesn't hold up. There's just too much North American affinities in either the detrital zircons or the fauna or some of the volcanic signatures or whatever in these rocks. So that's why I don't use that one. And of course, what I did is I used the Salibi's model for the south and the Canadian model further north. And of course, you know what they say, Confucius say men who stand in middle of the road get hit by trucks going both ways. So that's okay. It's fun to do this, and it's fun to get reactions and so forth. And so, anybody that thinks these maps are perfect is not thinking clearly. But on the other hand, they're not pure cartoons either. So the answer is somewhere in between. One more short question.
Sure. I wonder where you go from here. Do you go back further in time, or do you expand?
Okay. When I finished that southwest, I wonder why that isn't projecting well up here. These are very, very detailed maps. Anyway, the Southwest series I finished 8 months ago, and I decided I need to redo my North American series. Well, I got 97 maps in that series, and to redo every one of them, no. So what I'm doing is I am choosing about 40 key time slices in North American history. I'm showing them at 2.7 times the resolution of I think many of you are familiar with my North American series, 2.7 times the resolution of these. And so they're going to be super detailed. I just, night before last, I'd like to say I finished, but I know I haven't, the Mississippian, so that's how far I've gotten. I got a long ways to go. These are extremely time consuming. The larger the resolution, the more difficult they are to paint. And if you knew a lot about Photoshop, you'd probably know why that is, but it has to do with taking your clone target and bringing it into the map, and if you distort it too much, it looks bad, and anyway, so they're really time consuming. So I'm hoping, I said end of the summer, well, the end of the summer has come and gone, so I'm saying maybe early next year I'll have this new North American series. After that, I don't know. I get a lot of requests for Gondwana, for South America and Africa. I don't know a lot of details about that part of the world, but I also did a partial Australian series. I'd like to finish that sometime. Australia is the history there is just mind-boggling. I did a real early Asian series that I don't even post on my website because they're so crude, but it was one of my first attempts. And I'd like to redo that sometime, but you know, that is so complicated. The problem with showing Asia is no matter what map projection you use, you got bad distortion somewhere on your map. And dealing with distortion is a big pain in the butt, believe me. So that's why selecting my projection is very, very important.
Okay, so some of you probably want to go down and talk to Scott Tinker in 108. But if you want to talk to Ron some more, we can be in here for a few more minutes. So let's give him another hand for Triple.